Okay, so let's go ahead and continue on with our discussion of 2D kinematics. I found a really good write-up of the problem that's in the notes that's talking about this rock being ejected from a volcano. And you want to calculate some things like time and distance and whatnot. And I kind of briefly started talking about this on the last lecture, but I ran out of time and I rushed through it. So I found this this good step-by-step solution for it that I thought I would walk you guys through and show you how this problem works. The reason I like this problem is that it's relatively simple to do. It's a good application of our kinematics equations that we need, but it's got just enough complexity that you can use all of the skills that you have learned up to this point to solve this problem. And I think if you understand this problem and understand how to solve it, then you've pretty much got a good grasp on two-dimensional kinematics. A couple of things that I want to reiterate as we go through this problem that we're thinking about. A lot of times in physics, we tend to make assumptions about the problem that as physicists, we just kind of do intrinsically, but for some of our students, sometimes that may not always be evident. And so one of the things that we're going to assume here, again, is the idea that there is no air resistance. We're not worrying about any friction or anything. Another thing that is not inherently obvious in this diagram, especially this particular problem we're worried about, the projectile has dropped to a certain distance below whatever we picked as the horizontal, is that we are going to assume a flat Earth model. This does not mean that the Earth is flat. In case any of you flat earthers stumble upon this video 20 years from now. What this means is that, yes, these distances might be a little different if we account for the curvature of the Earth, but not by enough to matter. So we can model this thing as a flat plane. All that being said, it means that if you were to go and actually do a real analysis of this thing and using all those variables that we have assumed here, you're going to get a number that's slightly different, but it's not going to be all that much different. Again, this is an entry-level class, though, so we don't worry about those things. Now, having said that, let's look at this problem again. We have a volcano that has ejected some kind of hot volcanic rock. We know, well, first of all, we notice where we picked our coordinate system. We've picked X to be positive to the right, and we picked our Y direction to be up and down with positive up. We've also picked our level plane as the top of the volcano. This is going to be important later. Remember, when we set these equations up, we need to understand from a physics standpoint of what we're measuring, we need to decide where our starting point is. Generally, we think about the origin or the starting point as the intersection of these two axes. Now, what that means for us in this problem is that zero elevation is going to be the top of the volcano. That's going to be our zero and the Y. But notice that at the end of this problem, this rock is somewhere below whatever we chose to be the zero. So its position is actually going to be negative. That's okay. The only thing that we don't want to be negative in these calculations is going to be time. Because if time is negative, then that means that the event started prior to you starting to measure it, which means that you probably did a poor job of picking your origin. That's okay. Our zero in the X direction, again, is just going to be the top center of this volcano, wherever we started. We also know that the initial velocity of the rock that's being thrown out of this volcano is 25 meters per second. This is a question that comes up often. When do we mean this thing is traveling at 25 meters per second? I'm talking about the instant it starts moving. Yes, while it is in your hand and contacting your hand, or in this case, while it's inside the volcano, we're going to assume it has a velocity of 0. Just as soon as it gets any distance above whatever we pick to be our 0, that's when we start measuring our velocity. That's what we're going to call our initial velocity. So in this case, our initial velocity is 25 meters per second. It doesn't matter how it got there. It doesn't matter what it was doing prior to that. All we care about is that that instant, we're using 25 meters per second as the initial velocity. We also know that if we measured an angle between what we've chosen to be our horizontal plane and the angle that this rock comes out on a straight vector is 35 degrees. So that's all we need to solve this problem. So what we want to do, if you'll notice in this right up here, it gives you all this, and it says, let's find the time it takes for the rock to follow this path. So we're talking about the time it takes to go from just the edge of the volcano, just the instant it comes out, until it lands 20 meters down the hill on whatever we're calling the ground. So the way we're going to do that is by using our kinematics equations. So the first thing we're going to set up is this equation here. Now, when I have given this to you before, I've either used X or I've used S. Sometimes I'll use D. Remember, it doesn't matter. As long as you are consistent and as long as you understand what you're measuring. In this case, the thing that we know we can measure is the velocities and the angles. We're worried about the time it takes to travel this Y distance. So we want to first look at things in terms of Y. I'm not worried about things in terms of X yet. In other words, when it asks me to find the time, the easiest thing to do is find the time it takes to go from here to the top of the arc and then all the way back down, knowing it's going to travel a little bit further. That's okay. So instead of X or S or D, we're just going to use Y. So we have our Y position. Remember, Y without any subscript, that's going to be our final position. Our Y sub naught, that's going to be our initial position. Our V sub naught sub Y, that is going to be our initial velocity in the Y direction. T is going to be the total time it takes to travel this whole distance. We know it's the time it takes to travel the whole distance because Y is going to be our final position. If we wanted to know halfway, then we'd need to know what this halfway Y distance is. In this case, we don't care. We just know that our final position is going to be this, so we want the total time. So that's what T is. 1/2 is just 1/2. It's a fraction. We'll get into where that comes from probably in the next week or two when we start talking about energy. We'll talk about where this factor of 1/2 comes from and the square factor in this term. G in this case is the acceleration due to gravity. If you look at your generic equation that I gave you, instead of G, I have A. A is acceleration. In this case, we're assuming we're doing this on Earth. And so the acceleration that this object is undergoing is the acceleration due to gravity in the Y direction. Remember, we're doing everything in Y. So our acceleration in the y-axis is only the acceleration due to gravity, which we're going to call g. If we were to do this for x, understand the acceleration in the x direction would be 0, because there is nothing acting on this rock. As soon as it leaves the volcano, it's completely free. There's nothing that's pushing it forward other than whatever the initial velocity it had. So there's nothing accelerating it in the x direction. There is something accelerated in the y direction, and that's gravity. That's going to be true for most everything you do. So we got our equation. We understand why we're using this. Then we're going to take our initial position, why not, and we're going to let that be 0. Remember, we choose where our initial position is. I'm a physicist, I'm lazy, so I'm generally going to say wherever I start, that's my 0 position. What if I didn't do that? What if I said my 0 position is going to be down here on the ground? Well, it doesn't change anything. My y position, my initial y, is just going to be positive 20, because I know it's 20 meters away. So that's the only thing that changes. But in this case, we've chosen our starting point to be up here at the top of the volcano. So we're going to call our initial position 0 in the y direction. That means our final position is negative 20. Remember, because it's below where we've chosen our 0 axis to be. Had we chosen our 0 to be at the ground, then our initial position, or our final position, would be 0, and our initial position would be positive 20. Notice the only thing that changes is the sign, but the sign would change sides of the equation too. And since sign only means direction, because of basic algebra, that takes care of our sign problem. So if we look at what we know a final y, we know an initial y. We're trying to find a t, so that's okay, we don't know that. We know a 1/2, we know g, that's a constant. So we don't know what this v0 sub y is. But we do know what the total velocity was. We have to go back to the vector thing. We do a right triangle problem here. We have something traveling in a diagonal. That means it has an x part and a y part. What we want to know is the y part of the initial velocity. So if you look at the next equation, remember that the y component of any vector, in this case v, is going to be the total vector initial, so v0, times the sine of the angle, in this case theta naught. Now, the existence of a theta naught implies that there may be a case where the angle would change. And that happens all the time in the real world. In aviation, when we fly airplanes, we generally don't just hit the throttle, set the pitch, and climb. We generally will hit the throttle, we'll set a pitch, climb to some intermediate altitude, change our pitch, change our throttle, so our angle may be changing. Spacecraft do this all the time. This is how we get to orbit, is we launch kind of going vertically, and then we do what's called a gravity turn to kind of follow the curve of the Earth until we get into orbit. So our angle is changing in those cases. In this problem, our angle is not changing. There is nothing to make it change. So we're only worried about the angle that we launch this thing at. So that's our theta naught. So if we just plug what we know in, we know v sub naught, that's our 25 meters per second, we were given that. We know our angle, theta, is 35 degrees, so we know the sine of that. And if we plug these numbers into our calculator, remembering to be in degree mode, we're going to get a y component value of 14.3 meters per second. So what does that mean? It means that if we looked at just the up and down component of this thing, if we had some kind of camera that could track this thing only going up and down, and it was stabilized along the x-axis, we would measure this thing going up and down, up initially at 14.3 meters per second. So that's just the y part of that. You can easily find out, if you care, what the x component is, because we know the total component is 25 meters per second. We know the y component is 14.3 meters per second. Well, we know two sides of a right triangle. We can use the Pythagorean theorem to figure out the other one pretty easily, just using algebra. Or if you wanted to, you could calculate the same thing by saying V naught x would be V naught cosine theta. That would give you the x component. In this case, we only care about the y, which works out to be 14.3 meters per second. So what are we going to do with that? Remember, the reason we needed that is because we got to solve this equation. This y equal y naught plus v naught t minus 1/2 gt squared. Notice there's a negative here. And what I gave you was positive. This is because gravity acts in the downward direction. So we have a negative sign that we have to account for here because of the direction of gravity. That's okay. So that's where that comes from. No big deal. If you don't want to remember to put the negative sign there when you're doing gravity, write the whole thing down as just pluses. And when you put in your gravity, write negative 9.81 and it'll take care of itself. It's just algebra. So we needed to know what this variable v naught y was in order to solve this. Well, now we know what v naught y is. So we go back to our initial equation and we say our final y position is our minus 20 meters. Our initial y position was 0, so it goes away, plus our v naught times t. Well, we know our v naught is 14.3 times t. We need that. And then if we take our negative 9.81 times 1/2, you get a 4.9 meters per second squared, remembering your negative sign there, and times t squared. Don't forget the square in this thing. Well, we need to solve this equation for t. So how the hell are we going to do that? Well, you might be tempted to simply try to factor this out, do the FOIL method or something. But what you're going to find when dealing with these decimal values like this is that doesn't always work out for you. That gets to be nasty. So the other way we can do it is this formula you have never thought about since about 8th grade, the quadratic equation, the quadratic formula. We want to solve for t in this quadratic function. So remember this thing, that in this case, t is our variable. You might have seen it as x, is minus b, where these are coefficients, right? So you got your squared term has coefficient of a, you have your first power term that's coefficient of b, and you have a constant term with coefficient of c. So we are minus b plus or minus root b squared minus 4ac all over 2a. You did this in 8th grade and went, why in the hell am I ever going to need to know this? What am I ever going to do with this knowledge? Well, here's what it is. Here's why you need it. Because not all of these equations are nice, well-behaved functions. Many times you end up with these weird decimal values that are not perfect squares, but we need to know a solution. So we're going to use quadratic formula. So don't forget about quadratic formula. This will work if you don't remember how to do simple factoring and you get something that happens to be well-behaved and nice even numbers, and you don't remember how to do the FOIL method and factor like that. That's okay. You can still use the quadratic formula and it'll still work. Doesn't matter. So if we plug our numbers, we know our constant A is going to be 4.9. Our constant B is going to be 14.3. And our constant C is going to be 20. If we plug all those in, what you're going to get are two solutions, because you have a plus and minus here. You have to solve for both of them. So what you're going to get are two solutions. One solution is going to tell you that t, remember, our time is 3.96 seconds. And another solution is going to tell you your time is negative 1.03 seconds. Remember, we set this equation up and we set our coordinate system up so that things work out nicely for us. In these kind of problems, when we set this up correctly, we don't care about what happened prior to the motion starting. We only care about what's happened after the motion started. So we only care about positive values of time. So we're going to use time is our 3.96 seconds. So that's what we've solved for. Well, guess what? What were we asked to find? Calculate the time it takes for the rock to follow the path. We know the path is defined by this equation. If we know that is the equation of the curve that the rock follows, and we know our starting values, and we solve for t, we just found the total time. So we know how long it took for the rock to go from here, follow this arc, all the way down to here. And it works out to be 3.96 seconds. Cool. How can we use that information? We can use that information to find out all kinds of things. We can use that information to find out how high this thing went. Notice we weren't told that. We were told where we started, and we picked that as our 0, and we were told where we ended. But we might want to know what the maximum arc of this thing is. Well, that's pretty easy. We know the acceleration due to gravity. We want to find our y max, so we draw our same coordinate system with our x and our y here. If we go back to here and we look at this equation, our initial position is going to be 0. We want to know what our maximum altitude was. So our final, we don't know. We know our V0. We just found that. We know how long it took to go that far. So we plug in our T, and we know our acceleration due to gravity. So we plug that in. That's going to tell us the time it takes to get to our final Y position. Well, we already know the time. So that's going to, using that time, that's going to solve for what this position is. So we can use this information to find out things like that. Now, why do I care? So, flying story time. Back when I was much younger and much thinner, I used to fly combat aircraft in the Air Force. I was a flight engineer. And one of the aircraft that I engineered is called the C-5 Galaxy. It's a giant cargo airplane. We flew stuff in and out of Iraq and Afghanistan all the time. We were flying one time, this has been probably 10 or 15 years ago, and there was a volcanic eruption in Iceland. And you can look up the details of it. Like I said, it was probably 2012 or something. Anyway, if you don't already kind of have an intrinsic feel for it, volcanoes tend to be pretty bad for airplanes. Airplanes don't react well to them, particularly the dust, the volcanic ash. Airplanes don't react well to that. The reason is because volcanic ash is mostly made up of molten rock. It's not just dust. So if we were to fly through that, that molten rock would encounter the blades on our jet turbine and immediately cool. And so now you have a jet turbine that's coated with rock unevenly. And if you've ever had an uneven load in a washing machine, you know what that sounds like. Imagine what that does to a jet engine spinning at 36,000 RPM, revolutions per minute. That can be extraordinarily bad and cause you to die. So we generally try to avoid volcanic ash clouds. We also don't want to fly too low over the volcano in case it's spitting out rock and fire and things like that. I generally don't want to fly into it. So I might want to know what this height is. So that's why we would do this. Now, I didn't have to do it because I didn't have all this data, but meteorologists and geologists have this data, and they provide it to our flight planners, and they use this. They use physics to figure out, the maximum elevation of this is going to be at 25,000 feet. Well, cool. If I can fly my airplane at 40,000 feet, I can fly above it and it's not a problem. What if the height's around 30,000? That's generally where I cruise, is around 30 to 32,000. And I want to stay out of volcanic ash cloud. Need to know how high it is. So I'm going to plan to stay around it. I'm going to fly above it or around it. Or in our case, we stayed in Germany for about a week until all the volcanic ash cleared out, which was a much better option. And if you've never been to Germany, I highly recommend it. It's amazing. So this is how we solved this kind of problem. So here is a nice illustration of what's going on with this problem. If we were to just draw these arcs, notice this is pretty generic, as most physics problems are. This doesn't have to be a rock coming out of a volcano. It can be a cannon, it can be an artillery shell, it can be a rocket, whatever it is. We can draw that same arc. So if we know what the angle is, look what happens. The faster the velocity is as that projectile leaves whatever its origin is, the longer this distance is going to be. That makes sense. This is called range. So if you ever encounter a problem, and I think there may be one or two in the homework set that ask you to calculate the range of a projectile, that's what it's talking about, is this distance in the x. Well, how do we do that? We start it just like we did before. We need to know the total time that it takes the thing to move, right? Well, once we know the total time, instead of taking that time and plugging it back into the y equations for distance, we plug it into the x equation for distance. How do I know I can do that? Well, if we think about the motion of this projectile, we know that it's moving in the x and y plane simultaneously. So there's no reason at all that it should take it a greater amount of time to move from left to right than it does from our starting position to go up and then back down. Now, again, we're intrinsically saying the thing's not rolling when it hits the ground or something like that. It's just kind of going up and it's impacting the ground and just sitting there. So we already know intrinsically that those two times, the time it takes to travel the total x direction and the time it takes to travel the total y direction, must be the same. If they're not, then we have broken space-time. So since we know that, let me get back to this equation. If we start looking at x values here, if we say x equal x naught plus v naught x times t minus 1/2 gt squared, think about our volcano problem. Our final x position, well, that's what we want to know, right? That's our range. Our initial x position is going to be 0, right? We're talking about x now. So we started x naught here, And we want to know how long this line is, basically. We've already accounted for this drop. That's our y direction. So now we want to know this. So I know where I started at 0. And I want to find out whatever this x value is. So that's my range. So that value x is equal to our initial x value, which in this case is 0 because I picked it to be 0, plus our v naught x. Remember, we're talking about v naught x. We're not talking about v naught y. So now we need to know the velocity in the x direction. How do we find that? Remember, right triangle problem. Anytime you have that diagonal and you're asked to find the x and the y direction, think about right triangles. It's going to be a sine or a cosine. We use sine to find y. We're probably going to use cosine to find x. So we do that. And once you plug that number in, it becomes whatever it is. I haven't worked it out yet. But we know that v naught x. We know our time. We already found that to be that 1.38 seconds or whatever it was. We know our g is our acceleration due to gravity. Still know the same time. Well, look what happened. Now we have a nice clean equation that we don't have to do any factoring or anything. It's now just a standard algebra 1, plug numbers in, put it in your calculator, and you're going to find a range. Well, that's kind of cool because now I know how far away I need to stand from this volcano to make sure I don't get hit, because that would suck. Clearly, the guys that lived in Pompeii did not live beyond this. They lived over here somewhere on the edge of the volcano, and they got covered up in volcanic ash and lava. So we understand two-dimensional kinematics. I want to show you something. What's it called? You might have used this in high school, this PhET thing. So PhET is a really nice simulator for some basic physics stuff. Trying to find the projectile motion one. Circuits, waves, gravity curves. I mean, it's got all kind of stuff in here, but there it is, projectile motion. So what we can do is we can do the volcano problem in this, right? So we knew our initial speed in the volcano problem was 25 meters per second. We know that our angle was 35 degrees. We don't really know what the range is. So we can fire the cannonball. And oh, look at that. And then if we want to know how far that is, we just move this. And it works out to be 28.6. There's a way we can measure our vertical distances here. Yeah. Find that 6.5. And you can play with a lot of things here. So if this is using air resistance, if I remove air resistance and I do the simulation again, look what happens. We have much less drag and the thing goes way, way further. You can show all your components here. You can show your velocity vectors. So this is just a really fun simulation to play with. This is also a really, really great tool for you, nudge, nudge, wink, wink, when you're doing homework assignments that you can check your work when you do projectile motion problems. you can go into FET. You can remember to discount air resistance. We're not worried about mass, your velocity vectors. You can plug in your initial speeds and your ranges, and you can just run the simulation and it'll find those values for you. If you go to lab, you can do kind of the same thing. You can also play with gravity if you go to lab. So here's the cannonball on Earth under 9.8. What if we reduce this down to 5.4? It's pretty low. Look what happens. Much, much higher arc. What happens if we take this out to 20? So that's a little more than 2 Gs, so a little heavier than 2 times Earth gravity. Oh, cool. Well, we know that sometime between here and here, we can hit this guy. So I can play with gravity and see if I can hit him. Yeah, all right, no, I missed. This is why I was in the Air Force and not in the Army, because I don't know anything about projectiles like this. So we'll do that. Anyway, you can kind of play with this and see if you can hit this guy. If you wanted to map that out, you could absolutely do that. You simply move this target, and we know our range is 7.1. We can set our angle, in this case was 80. We can set our initial speed. If you do the math, you can figure out exactly where to place this target and then run the simulation. And if the cannonball lands on the target, you did the math right. So pretty cool little simulation. I will use this periodically to show you some things in class, and I might post some things for you on Blackboard to play with it, especially as we get into more and more complex things. They've got a really good one for energy when we start talking about potential and kinetic energy. That's very useful. So this is a good way to practice kinetic energy or projectile motion problems. I'm going to show you one more thing. I'm not going to do this today, but I am going to do it Friday. Let's see. No, it's not cliffhanger. Yeah. So there was this movie called Skyscraper that came out, I don't know, several years ago with Dwayne Johnson. I do this with my students at Governor's School. We can take a look at this movie poster, and we can see that we have Dwayne Johnson here. He's clearly just run off of this scaffolding, and he's trying to land in this window. Now, I haven't seen this movie, but I've seen this movie. You know what I mean? We all know how this scene plays out. Big muscle man hero runs off the scaffolding and barely catches the ledge of that window with his fingertips, and he climbs up and, you know, gets in the building safely and goes and hunts down the bad guy. I submit to you, by looking at this poster, that whoever designed this poster knows nothing about physics, because he's going to die. And what we're going to do Friday is I'm going to analyze this. We're going to work on this. We're going to do the projectile motion problem from just this picture. And the result is going to be exactly what you expect, that he's going to die in a loud, violent military manner. But I think it is a pretty fun exercise to do. I think it's a good exercise in how to set these problems up yourself when you don't know anything. All you have is a picture. This is very, very common in most applications of engineering and science and that kind of thing. We kind of just take the world around us and we measure things. So in order to do this, what we're going to have to do is we're going to have to figure out some distances. And we're going to have to find some velocities, and we're going to have to find some times. We can do that just from this image. And it's really not that hard. But again, I think it's kind of a fun little exercise. So that's where I'm going to go with this thing on Friday. Does anybody have any questions before I stop today? No. Okay, then this lecture will be posted up on the YouTube channel here in the next hour or so, probably. If you have questions, feel free to email me, set up time, come talk to me in my office. If you're struggling, I've already had several of you do that. That's great. Homeworks seem to be coming along fine. A few of you look like you're a little bit behind, but most of you seem to be doing fine with that. I expect our first test probably next Friday is kind of what I'm thinking. So in about another week, you should have your first test. And as long as you have been doing the homework, you'll be fine. The first test, by the way, is going to cover just the first 3 chapters. So everything that we talked about at the beginning, like unit conversions, measurement, that kind of thing, precision, that will be on there, as well as one-dimensional motion, throw the ball straight up in the air, and 2-dimensional motion, which is the cannonball problem or the rock falling to his death problem. That's all that's going to be on the test. You can see now, I think, that there's not a whole lot of equations here. So don't expect any surprises. If you can do the homework, you'll be fine on the test. All right. So having said that, I will see you guys in the next lecture.